Good afternoon. I'm Darryl Pinkins. We're here to introduce Dr. Mark Perlin, and he is the Chief Scientific and Executive Officer at Cybergenetics. His company, Cybergenetics, was founded in 1994. The initial focus was genetics, using computers to automate DNA interpretation. By 1999, the company transitioned into forensic analysis to address backballs and solve the DNA mixture problem. The TrueAllele technology helped identify victims' remains in the World Trade Center disaster. 10 years of refinement led to routine use in criminal cases. Now attorneys may use cybergenetics, probabilistic, genotyping to find truth in the DNA.
We are thankful, very thankful, for the truth and for Dr. Perlin. This science provided by Dr. Perlin and his company, pro bono, to our defense team led to our exoneration. And when I talk about him, I get shook up, because he's a lifesaver. Dr. Perlin has testified about computer DNA evidence in state, federal, military, and foreign courts. Holds doctoral degrees in mathematics at the University of New York and computer science, Carnegie Mellon University, and a medical degree at the University of Chicago. In October 2017, Dr. Perlin was presented the Champion Award by the Foundation for Improvement of Justice. So I would like you all to give this to Dr. Perlin a round of applause. This man is saving lives.
Thank you. I don't know I'm going to be that rousing. Okay, so most of this presentation was something that I'd prepared for a post-conviction hearing in 2016. And I gave this presentation in rehearsal at Duquesne Law School to an evidence class. And I'll show you what I was talking about. This slide wasn't part of it. This is the basic background. And the focus of this talk, the way I presented it, was on Darryl Pinkins, because that was what the hearing was set for, though it applies equally well to Roosevelt Glenn. So in 1989, there were 5 men who raped an Indiana woman. There's a whole story of this, of the bump and rapes and how these crimes were crescendoing in northwestern Indiana. And Darryl Pinkins, Roosevelt Glenn, another man, were misidentified. There's a whole story there. And in 1991, Mr. Pinkins was wrongfully convicted and sentenced to 65 years in prison for a crime he didn't commit. And Mr. Glenn was convicted as well. In 2001, there was DNA evidence that was found. And you would think that would be the end of it. There's DNA evidence that shows that there's 2 genotypes, DNA from 2 individuals who are not the accused. And for some reason, in Indiana or wherever, the post-conviction court decided that if there were 5 attackers, you needed 5 genetic types. And that was what would be needed, and post-conviction relief was denied. So this is where I started educating the law students, and this is what we use with juries. So I'm going to start with DNA biology. This is all at a level that you should understand. So the human body is made of trillions of cells that have nuclei, and as shown on the left, there's a nucleus inside of a cell. The nucleus is where the DNA is, and we all have 2 copies of that DNA, one from each of our parents, mother and our father. And if you were to look at the whole genetic complement that you received from one of your parents inside one cell, it's about 3 billion DNA letters. They're written in a chemical alphabet with 4 letters, and they're nicknamed A, C, G, and T. That entire encyclopedia of DNA is packaged up into 23 volumes. Each one's called a chromosome. And if you were to unravel a chromosome and look at it under a microscope, you see that it's just text, like a hard drive or a book. It's just text. You read it. And what's shown on the right is a location. Someone pointed this out to me. When you look under a microscope, you don't see the letters A, C, G, and T. That's just something that we annotate with. They're molecules that the human cell can read, and there are 4 different varieties. But the point is, each location is like a paragraph of text. For human identification, the main type of text that's looked at is a type of genetic paragraph called a short tandem repeat. I'll explain to you where that comes from. So here we have our 23 volumes, our chromosomes shown on the left, from one copy of the genome. We have 2 copies in each cell. And scattered throughout the genome is about 100,000 locations that have a paragraph on that page of some volume that's the same for everyone, with one slight variation. In the center of the paragraph, there's a word. In forensics, it's usually 4 DNA letters. That's repeated some number of times. It's a short word, 4 letters long, and it's repeated in tandem, short tandem repeat, or STR. And that's where the variation is. That's different between different people. At one of these locations, there will be maybe 15 different lengths that occur in the population. And those differences can be used to identify people and distinguish between them. If it was all the same, you wouldn't be able to do that, but it's the genetic variation that lets us identify and distinguish people. This is what it looks like on the right side. There's a starting section. This is, again, English, not DNA-ish. Take me out to the ball game, take me out to the crowd. That's all the same. Then you get to this repeated word, root, 4 letters that just keep repeating, and then it continues, and it's fixed again. And what's interesting about this is, though all the paragraphs may be the same, if you look at the number of times the word root is repeated, changing the number of repeats, which is the genetic variant, is directly related to the length of the paragraph. Here, root is repeated 10 times, so there's some length to that paragraph from beginning to end. If there was an 11th occurrence of the word root, the paragraph would be 4 letters longer. And what scientists can do is they can measure the length of the paragraph and work backwards how many times the word was repeated. So if you know the length of the paragraph, you know how many repeats there are, and each genetic variant, called an allele, is the number of times that the word was repeated. It's different in different people. In this case, the allele is 10 because the word's repeated 10 times. The key concept, and Fran put it into the title, is genotype. So the genotype is the barcode that scientists look at. They have maybe 15 to 20 different locations from independent paragraphs on different chromosomes across the human genome. And scientists will look at the genotype, the pair of alleles that you've inherited, one from each parent. And if you make a list of those allele pairs at 15 different locations, it turns out it's relatively unique, and this is why. So at one of these 15 locations, you have 2 copies in every chromosome with this location. So in every cell, you have, at the same volume on the same location, if you were to be able to look at that genetic page of that cell, you would see the mother allele and the father allele. That's what you've inherited. You have that throughout your body. It pretty much doesn't change. Here, we saw that at that location on the mother page, from a volume on a paragraph, there are 10 repeats. You look over in the cell, what does the father provide? Well, maybe at that location there's 12 repeats. That pair of alleles, what you've inherited from your mother and father, those two alleles, that's your genotype at that location for a person. And so in this case, that would be a 10-12. Now, that's a lot of variation because if you have 15 different repeats, 6, 7, 8, 9, 10, 11, 12, 13, 14, throughout the population, then 15 times 15 over 2 is roughly the number of distinguishable genotypes. So a 7 and a 10, a 9 and a 15, whatever that pairing is. A 9 and a 15 we can't distinguish from a 15 and a 9. That's why we divide by 2. So there's about 100 different genotype values, like 10, 12, or 11, 17, at each location. And these are independent. So if you're looking at 15 locations, 100 possibilities at the first location, times 100 at the second, times 100 at the third, 15 times. Each one gives you 2 zeros. That's like a 1 followed by 30 zeros. That's a lot of genotypes. That's a lot of barcodes. There's only 7 billion people on Earth, which is a 1 followed by 10 zeros. So these barcodes that we inherit are relatively unique. And except for identical twins, they turn out to be pretty unique identifiers for people. There's just so many more barcodes than there are people. Okay, so this is where DNA is easy. We're going back 20 years ago when evidence was lots of DNA from one person, a pool of blood on the floor, like in the OJ case. Just lots of DNA from one person. We'll move on to more complex DNA at some point, but I want to start with that. So on the left side of this picture, we have a double-stranded helix that's indicating there's DNA from one person. How do you get the DNA? Well, you can have clothing and cut pieces out of it. You can have a rape kit and have a swab and cut pieces out of it. You can have a handgun and you can swab it. There's different ways of getting DNA. You can have a reference sample from a person and take a cheek swab. Lots of DNA from one person. What the laboratory does is they have 3 steps. First, they take whatever biological sample they were given and they extract the DNA out of the biological sample. They do this by breaking open the cells and then separating out the DNA molecules through different means, chemical or physical. Now they're holding on to the DNA that was in that biological sample. Then they take that DNA and they amplify it and they make millions, actually billions of copies. There's a chemical reaction that I won't be talking about today that is the main amplifier for DNA in molecular biology. It's called polymerase chain reaction. It's a chain reaction because it cleverly keeps doubling what you have. So you have a little bit of DNA and then you have twice, 4 times, 8 times, 16 times. And after 28 cycles, you have like a billion-fold amplification. And so you can take a very small paragraph of DNA and amplify it, put fluorescent tags on it, and now this small amount of DNA that may have represented 50 cells, you can now see with instruments. And the third step is to use that instrument. It's a DNA sequencer that can separate these amplified fragments by size and measure how much fluorescence is at each fragment. So again, you extract the DNA, you amplify it, and then you detect it. And the kind of signal you get, I'm showing you in the center of the picture. This is just a cartoon. We'll see real data later on. If there's this genotype at this one location from an individual that has a 10 and a 12 as the 2 different variants, and nothing else, because it's just one person's DNA, what you see on the picture is that the DNA is separating by size, you're not seeing anything, and suddenly there's a 10. There's an event that there's a paragraph that had 10 repeats. And then further on, you see the longer paragraph that had 2 more repeats. And that's the 12 that you're seeing on the right. You're not seeing an 8, a 9, a 15, or a 17. The only two alleles that are present in this person's genotype are the 10 and the 12. You're seeing the two peaks. That's what the data looks like. This kind of data is really easy to interpret. Because of the 100 possibilities, you can look at what is possible for one person. Is there any support here for an 8 and an 11? No, there's no data that supports it. Is there any support for a 12 and a 15? No, because you're not explaining the 10, and there's no 15. Of the 100 possibilities, the only explanation supported by the data on a simple reference sample like this is a 10 and a 12. That's how you infer an answer. How well do these different genotypes explain the data? Of the 100 possible allele pairs, the only one that's explained by the data, as shown on the top right, is a 10-12. So that's the genotype of this person at this one of 15 different locations. To make it simpler, you look at the data, you see a 10 and a 12, that's the genotype. Right? That's what you see. It's very straightforward when there's only one person in the DNA sample. And then, as shown on the bottom right, you can make a comparison. If you compare with a person whose known genotype at that location on that chromosome is a 10-12, then you have a match, and you can work out a match statistic. It's 1 over how rare that 10-12 is. That's basic DNA the way it was 20 years ago. And we'll stick with that for a little bit because that was quite relevant in this case for much of the evidence. We'll have to move beyond it a little bit to complete the story. So what this story is if the post-conviction review court wanted 5 genotypes, how from the evidence that was collected at the time can we see 5 genotypes? Can they all be inferred from the evidence? What's obvious? What's less obvious? What's going on? There are 2 main evidence items. The first was a jacket, and the jacket had a semen stain on it. And so shown on the left is the jacket. And then you see there are these 2 arrows that are making a separation. That's because a very old technique in DNA, over 20 years old, is a way of separating sperm cells from non-sperm cells, like the victim's skin cells, the epithelial cells. That's possible because the sperm cells are much hardier and packaged up. And so by breaking open the cells in a gentler way, you can first break open the non-sperm cells and separate them, and then afterwards separate the sperm. So all labs do this who do DNA analysis. And on the bottom, we see that there was a non-sperm fraction. It was separated into a non-sperm fraction. That had mainly the victim's DNA. We're going to refer to that with a V. I'm going to use letters here because writing it out won't fit on the slides. So V is for victim. That's in green on the bottom. On the top, in blue, there was a sperm fraction. And what the laboratory that looked at this evidence in 2001 saw from that sperm fraction was a 90% to 10% mixture. Now, the way mixtures are usually interpreted, which I'll talk about a little bit at the end, is by ignoring most of the evidence. And I'll come back to that at the end. It's much simpler for people to simplify data and give a partial answer than it is for them to pretend they're a computer, which they're not, and try to give a much more rigorous answer. And so in this example, because 90% of the sperm fraction corresponded to one person, the other 10% was very low level. The lab wouldn't know what to do with it. But they could look at the 90% and say, looking at the very tall peaks from that one person, we can pull out a genotype from the person who left most of the DNA, 90%. And that's what the lab did. There were no major statistics reported, but they found one person's genotype from the sperm fraction as a major contributor, and that did not connect with Mr. Pinkins. Now, this is not what they did, but what I'm going to be doing over the next half hour is building up a match table, or actually a non-match table. So let me tell you what these tables mean. In the rows on the left, there's only one row so far, but I'm going to keep building it up. We're listing the evidence items. In the columns, we'll be listing references and at some point other evidence items. And then the numbers in between are making comparisons. If the number is 0, it means there's no information either way. If the number is a positive number, it's a positive association. If it's a negative number, there's no association. It's a negative association. You can think of a positive number as the support for an inclusion, or an actual match, and a negative number as a support against a match. What do these numbers mean? They're the number of zeros in the match statistic. So 1,000 is a 1 followed by 3 zeros. If there's a 3 in the table, the match statistics is 1,000. 1,000,000 is a 1 followed by 6 zeros. So a 6 in the table would mean a positive association of 6. Here we see a number like -18. That's 1 over a 1 followed by 18 zeros. That's basically an exclusion. That means the person statistically just isn't there. How strong is the exclusion? Well, a match between this jacket and Darryl Pinkins is 1 over a billion times less probable than a coincidence. He's not there. Okay, so big negative numbers mean somebody's really not there. 1 followed by 9 zeros is a billion. So 9 plus 9 is 18. That's why it's a billion. Are you with me on that? That's as far out as the math is going to get. There's no equations. But big negative numbers means they're not there. Big positive numbers would mean they're really there. And if you think 1,000,000 is a big number, then -6 would mean somebody's not there. If you think 1,000,000 isn't a big number, well, you think something else. You're entitled to think whatever you'd like, right? You'd be a trier of fact. Typically in court, once you get to thousands, millions, billions, you're fine. So what you're seeing is this genotype from the jacket in J, when compared with the victim in column V, gave a number, I won't read the fractions, -15, 1 in a quadrillion. This did not come from the victim. It's a big negative number. Person's not there. What about Mr. Pinkins? Well, if the number were a big positive number, we'd be done. Or you'd be done. But it isn't. It's -18. He's not there. The association is 1 in a billion. He's not there. Okay? This isn't what the original crime lab did, but this is what computers can do. There was also a sweater. What do we see from the sweater? Well, the lab separated that DNA again into a sperm fraction and a non-sperm fraction. The non-sperm fraction shown at the bottom in green is again the victim. Now this sperm fraction looked like a 2-person mixture with an 80% major component, which we'll call S for sweater, as opposed to J for jacket, and a minor contributor that the crime lab couldn't interpret because it was too low and they don't really interpret those. But this major contributor was another piece of evidence, and it didn't match Darryl Pinkins either. So between the jacket, J, not matching Darryl Pinkins, and the sweater not matching Darryl Pinkins, the crime lab had found 2 items of evidence, 2 genotypes they could produce that didn't match Darryl Pinkins. And now, in a more modern computer sense, what we've done is we've added another row. The first row, J for jacket, we saw before. I throw some pictures in to make it easier so you can follow along in case, like, what is J, what is S, what are we talking about? S is the sweater, and here again, -15. How strongly is the sweater associated with the victim? Not at all. -15, 1 in a quadrillion. How strongly is the sweater associated with Darryl Pinkins? -15. Not at all. 1 in a quadrillion. Again, this is what computers did much later on. So these were the easy references, and this is a document that Fran provided me. This is the Court of Appeals saying, nah, 2's not enough, you need all 5. Give us all 5. DNA isn't exculpatory unless you fully account for the entire crime. Okay? From the Roosevelt-Glenn case, there was this extra hair that was found. And we'll call that H for hair. And that was also genotyped at some point. And now we add a third row, H, for the hair. We'll also add a third column for another reference for Roosevelt-Glenn. We see in the third row is that what's the association between this hair root with DNA and the victim? -15. It's not her. What about Darryl Pinkins, P, in the center column in the bottom row? -18. The strength of support is 1 in a billion. No, it's not him either. Now, we also are bringing in Roosevelt-Glenn's genetic types, and he just is coming up -15, -15, -15. The non-association is at the level of 1 in a quadrillion. This is, again, using computers to determine exclusionary match statistics. The methods in use at the time and by most crime labs still in the United States can't produce exclusionary statistics. They're designed to include people. That's all they can do. In fact, the name is a probability of inclusion. An exclusion is done by somebody looking at the data, not by producing a statistic. If you're looking at exclusionary statistics, this is newer computer technology. It's not what crime labs are doing at the time. So what do we have at this point? Jacket, sweater, hair, 3 evidence items, and they're not connected through the DNA with the victim, with Mr. Pinkins, P, or Roosevelt-Glenn. I think we'll turn into G on a slide soon to save space. Okay, well, 3 isn't enough, right? The PCR court, they want 5. You're going to have to continue. But first, we see something really interesting. Most, even software for DNA, can't get a match statistic comparing evidence to evidence. But some technology can. We saw something really interesting. When we compared these genetic types, which were basically, when we were done with it, looked like they were from one person. 2 were from a mixture, but they were very definite genetic types. That is, they were pairs of alleles. I'll show you fuzzy ones in a minute. We compared the genotypes of the evidence with the evidence, genotypes of the evidence. And the result is this table. If you look in blue down the center, that's just comparing the jacket with the jacket, that's the 11. The sweater with the sweater, that's a 10. The hair with the hair, that's a 10. That's what you expect. It's the same genotype. There's big numbers associating them, like 10 billion, 100 billion. But why would J and S, why would the jacket and the sweater be associated? Look at that 1.2. That's a number over 10. Look at in the first row all the way on the top right, the J and the H. Why would the jacket genotype be associated with the hair genotype? That's 4.5. It's in the tens of thousands. It's a different genotype. It's not at the level of 10 or 11 like we see in blue. It's something different. But they're really close. They're not big exclusions, and the numbers are close to each other. And Fran had this amazing idea, I thought it was amazing, which was maybe they're related. Dr. Perlin, she asked, is there something you can do with your computer to test to see if these people might be brothers, might be related to each other? And the answer was, sure, Fran, why not? First, why were these genotypes similar? Remember, I said that at each location, there are about 15 different alleles, different variants, like 5, 10, 11, 12, 13, 14, 15, 15 of those. That's not what we're seeing here. If you look at the top row, first of all, this is what determines the gender. This is why they're male. See, there's an X and a Y. Having an XY indicates that somebody's male as opposed to an X and X. And so each of the colors corresponds to the genotypes of one person from one of these evidence items. Red is someone from the jacket. Green is the person from the sweater. And blue is the person from the hair. The key is shown on the right. So every one of these people, the red are X and Y. The sweater isn't green, is an X and Y. The blue is an X and Y. They're male. So if there's a relationship, they would be brothers. There's no sisters here. Now if you look at the third row to D5, there are 15 possible alleles, and there's only one here. It's a 13. And every one of these people has a genotype that's 13, 13, 13, 13, 13, 13. They all have the same genotype. There isn't a 12, 15. There isn't an 8, 17. So, the chance of that is quite small, since there's 100 different possible genotypes. They all have the same genotype. If you go down to the fourth row, D7, you see that, again, they all have the same genotype. They're all a 10 and an 11. You see a red box in the 10 and a red box in the 11. A green box in the 10, green box in the 11. Blue and blue. Basically, these people have almost the same genotypes. Well, statistically, what can we do? This really suggests they might be related. We can do a kinship analysis. This is a family tree of the type you might have seen in grade school. So imagine that shown on the bottom left in blue, that's the box that corresponds to the genotype, the male genotype that we're looking at. We can have the computer say, all right, well, the sibling or the brother of that individual in blue, which we'll infer in red, we can have the computer figure out what the mother's genotype is, the father's genotype, from that known person from the evidence and other population information, and come up with a fuzzy genotype for the sibling. This type of math goes back to before 1940, of how do you figure out probability genotypes of relatives. And so in red, we're working out the genotypes of the brothers. And now in the rows, what I'm showing is these computer-inferred genotypes of the brothers. In red, we're seeing the sibling, the brother of the jacket genotype, the sweater genotype, the hair genotype. And now in the columns, we have the original genotypes. And when we do the comparisons, we're getting numbers like 3, 4, and 5 zeros after the 1. 1,000, 10,000, 100,000. That's the type of numbers you see with brothers. So statistically, it's much more likely that these individuals are brothers to each other than that they're strangers or unrelated people. Okay, so this suggests that tooling around the roads of northwestern Indiana was a gang of 5 people, and 3 of them were brothers. You guys brothers? No. So remember, this is a wrongful conviction lecture. As fascinated as you are by all this. And now when we look at the match table, we're comparing these 3 evidence items, jacket, sweater, and hair, as the rows, and then to the references, victims, Pinkins and Glenn, V, P, and G. And now we're accounting for the comparison with the evidence items. The reason I did this is you could say there's a positive association, and the court might rule, well, these must be the same people. You haven't distinguished them. Wrong. We have distinguished them. The genotypes are different. And the reason why the numbers in the right part of the table have some positive values is because they're brothers, most likely. They're different genotypes from different people, but because they're related, we're not getting numbers like negative 15 anymore. There's a genetic association. Okay, 3 down, 2 to go. But now we're going to leave the world of ancient, simple, single-source DNA from one person. We're going to move to the DNA that we get for most evidence now, and that's mixtures. What's a DNA? Who's heard of a DNA mixture? Okay, so DNA mixtures arise when two or more people leave their DNA someplace. Think of a sexual assault, right? You would have a victim, you would have an assailant, you can have a consensual partner, you can have 2, 3, or 4 people all mixed together in that DNA that the lab is analyzing. A handgun usually has about 5 people on it. Criminals love sharing. A hat will have 5 or 6 people on it. Criminals' underwear just happens to, criminals share a lot of things. Don't know why, but we see it in the DNA. Doorknobs may have 6 or 7 people. This device, which now 3 people have used, will have a mixture now of 4 or 5 people's DNA. Most DNA evidence is mixtures. And so DNA mixture interpretation. So now on the left of the picture, we have a cartoon showing, say, 2 people having contributed their DNA. The lab does exactly what it always does. It extracts the DNA. It amplifies the DNA. It separates and detects the DNA. The process is the same on all biological samples, and in the center, we see evidence data. We no longer see just 2 peaks of equal height, or 1 tall peak, if the alleles are the same. We don't have a genotype from 1 person anymore. It's from a pair of people. I'm not going to go into what the computer does. You're not interested. Oh, you might be, but not today. So let's just assume, but I want to give you a flavor of it. Let's assume that we know that the first contributor is a 10 and a 12, and we want to know what that second contributor's genotype is. What's that second person? And it comes down to how we can explain the data. If you said, well, the second person is a 7 and an 8, well, we don't see any 7 and 8. We only see a 10, 11, and a 12. And we're not explaining the new 11 peak. So what's old is the 10 and the 12. What's new is the 11. What it comes down to is, how do you account for the new 11 and the fact that there's nothing else there besides the 10 and the 12? And if you look at the possibilities, it can be an 11 and 11, a 10 and 11, or an 11 and a 12. And that's written on the top right. So out of the 100 possibilities of allele pairs, the only 3 possibilities with any appreciable probability associated with it, are those 3 shown. And then they have probabilities associated with them, probabilities being numbers that add up to 100%, or 1. How do we get at those numbers? By how good the explanation is. If I have equal amounts of a 10 and a 12, added to another person that's an 11 and a 12, then I'll get a pattern that we see of low, low, high. Right? There's 2 doses of 12, whereas there's only 1 dose of 10 and 1 dose of 11. So that's why the 11 and the 12 has more probability at 50%, because in combination with the 10 and the 12, it can better explain the heights of the data. More DNA, taller height. Less DNA, lower height. Good silence, there's lots of reading material, it's fine. But the idea is, what better explains the data, what doesn't explain the data? If you can't explain it at all, the probability is close to 0. Ways of explaining the data better, we'll see another picture of that, can give higher probability. Now when a comparison is made to a known genotype, we've separated out at this 1 of 15 locations that second individual. The math is the same for match statistics. If we see a 10 and a 12, compared with the 10 and the 12, now instead of being 100%, it's only 50%. That reduces the match statistic by half, by 50%. If what's on that list has a certain probability, then that's how much the match statistic is reduced by. It's not very complex. You just multiply by the fraction. All right. The reason this says computers can use all the data is because people don't use all the data. The standard methods of mixture interpretation are all about, when do you throw out the data? When do you throw out the data peaks? How do you consider them to all be the same height? Which tests do you keep? Which tests do you throw out? And you can imagine that in labs that are looking at a defendant, while they're trying to figure out which evidence to keep or throw out, there can be bias, which is a completely different talk I won't go into today, but scientists like Greg Hampikian, who got me involved in this case and introduced me to Fran, have written about this and talked about it and shown the impact of bias through human methods of picking and choosing data, which is horrible, but not for today. It's not part of the story. So in a picture like this, imagine that on the bottom left there's a small peak at 8. That might get thrown out and not considered. Or a small peak like 14 on the bottom right. Human scientists would decide, based on their lab protocols, that isn't data. They'd also might say that the 12 and the 13 shown in the center are both over a threshold and they're the same height. Now you look at it, they're not, but that's what the protocols are. So computers can use all the data, and what we're looking at is a signal like the one we saw before, where from left to right we have increasing DNA sentences, and we see a little peak at 8, a little one at 12, a bigger one at 13, small one at 14. The height of the peak is related to how much DNA is present from that allele. And computers can make tremendous use of these patterns, the heights, their variation, in order to explain this data. And I'll show you an example of an explanation. The way the computers actually think about these problems is they may try out 100,000 different explanations. They'll try out 100,000 different combinations of genotypes in different amounts. I'm going to show these to you as rectangles and then compare them with the data. They don't draw the pictures, they do it with math, but it's easier to see the pictures than the math. So looking at that same data, here is one explanation. Suppose in blue there's one person's allele pair, a lot of a 13-13, and they stack up. There's a lot of that one. And adding it up, you get a lot of that. So there's a big amount of that blue person's genotype. Then in orange, there's a little bit of an 8 and a 12. That's their allele pair from a second person. Put that down. And maybe a third person shown in green has a little bit of a 13 and a 14. And those alleles just keep adding up. If you look at the top of the stacks, you'll see a little bit of 8 in orange, a little bit of 12 in orange. That 13 has two big blues and a green 13, the top, and then 14's little. The height, that pattern that you're seeing of small, small, tall, and small in the blue rectangles is the same as what you're seeing in the data. That explains the data. That, therefore, confers higher probability to this explanation than to an explanation that wasn't talking about these peaks or didn't resemble the data when you added the peaks together. That's what the computer is doing. And because it's a computer, it can try out 100,000 possibilities objectively, whereas a person doing a procedure like this typically would take, on a simple problem, 2 days to try out one explanation. There was a lab that did that once for a short amount of time. Okay. Something else that we can do with computers is a joint data analysis. When we look at evidence, usually you don't go to court with one piece of evidence. You might, but usually not. And you have multiple items of evidence. A computer can look at different items of evidence together and statistically make a determination. That's called a joint data analysis. Here, it turned out that from that semen stain on the jacket, the laboratory made multiple laboratory tests, different amplifications. Shown in the top half is one amplification. In the bottom half, notice how there's an 11, little 11 peak in the center that we didn't see in the top. The computer can try to explain both of those together and often get more information. And in this case, when it did that, it produced an evidence genotype. So to back up what's going on, there's a mixture on this jacket. The 90% major component is obvious. It was reported by the lab 15 years ago. But what about the minor components? We're trying to pull out all the information here. So this is a small 5% component. This is one of those minor contributors that most crime lab methods ignore. And what we're seeing here is a genotype for this new contributor at one location. And it's what you saw before, but now it's a picture. It's different allele pairs with certain amounts of probability. Not showing the other 90 possibilities, but for example, in the center, there's a 12-12 with 45% probability. Next to it, over the word allele, is an 8-13 with 1% probability. The computer knows that looking at all 100 possible allele pairs for this second person at this location, that this is where the probabilities are after having seen the data. I will not talk about Bayesian computing and all that, you don't care, but these are methods, various groups do them, it's the most common way of getting information out of data across all fields of science and social science for the last 20 years. This is how people get information from computers. So what it does is it concentrates the probability where the explanations really do explain the data. And it lowers probability where it doesn't explain the data. And this is what a real genotype looks like. It has uncertainty, and the uncertainty is expressed with probability. If you want the information, you have to live with the uncertainty, but it can be quantified. And now what we're going to do is to compare this evidence genotype of this 5% small, potentially fourth contributor with coincidence. And the coincidence will be shown as brown bars. And what the match statistic is the ratio of the evidence blue probability divided by the brown coincidence for any possibility. Take a look at that 12-12 that's sort of near the center. There, the evidence probability in blue is 3 times higher than coincidence in brown. That's a match statistic of 3, because it's 3 to 1. If you were to take a look at 12-13 over the word pair, you'd see that brown is roughly twice the height of blue. That means coincidence is twice as probable as this evidence being attached to a person with a 12-13 genotype. That would point away from the person. Here, when we actually compare Darryl Pinkins' DNA, he happens to have a 12-13 genotype at this location. The chance of a coincidence is 19%, whereas the chance of the evidence having that 11-12 is 1%. 1 divided by 19 is around 1 over 20. That's pointing away from Darryl Pinkins, because that 1 over 20 is a lot less than 1. 1 would be as if they're equal, and then you don't have any information at all. So doing this at all 9 locations that were tested in this case a long time ago, crime labs now look at 20 locations, but this is old DNA evidence. We're seeing the results of 9 tests. The test names are listed from top to bottom on the different rows, and then the bars are showing how big the match statistic is. It's sometimes called a likelihood ratio. Long bar is a more inclusionary statistic. Short bar is more exclusionary. And when you multiply all those numbers together, you get the match statistic, which in this case was about 1,000,000 times less probable than a coincidence. So the computer produces a number, and then we can say that a match between the jointly analyzed jacket cuttings and Darryl Pinkins, looking at all of the jacket evidence from this contributor, is 1,000,000 times less probable than coincidence. Why did we do all that? We want a 4th genotype. We want to compare it with everything. So now there's a 4th row. And that 4th row, JJ, for the jacket looked at jointly, is now compared with the victim. It's not the victim, negative number. With Darryl Pinkins, negative 8.5. That's around 1 in a billion. With Roosevelt Glenn, negative 8.5. Again, around 1 in a billion. It's not them. But importantly, it's also not the other 3 evidence items. It's not J, S, or H. Those numbers are negative as well. On the bottom, -6, -5, -3. We found a fourth genotype. This is a fourth genotype. Are we done? No, the court wanted 5. So we continue. And now we have the computer look at the jacket and the sweater jointly. Remember, the sweater produced an obvious 80% genotype. It was just like really clear, very tall peaks. What about the smaller peaks? The computer analyzed those as well. And this is an example at one location. Shown in dark blue is the genotype probabilities of different allele pairs. And you see the pattern of the blue bars. That's the genotype value. Light blue is this new 10% minor contributor that we got by looking at the jacket and the sweater together. And if you look at it, the dark blue pattern from one genotype is different from the light blue pattern from the jacket and the sweater genotype. They're different. That's a fifth genotype. And now if you look at the bottom, there's JS, and does it match any of the references? Well, in the bottom row, for V, P, and G, the victim, Pinkins and Glenn, -10, -5, -12, it's not them. What about the other evidence? If you continue looking across the bottom row, it's not the other 4 genotypes either. It's not J for jacket, S for sweater, H for hair, or JJ for the jacket. This JS, jacket sweater genotype, that's a 10% minor, is new. So we've now identified 5 genotypes, which is what Fran was asked to do. Please, Fran, said the court, come up, bring me the broomstick of the Wicked Witch of the West. And she produces it. Okay. And now if you look at the columns for Mr. Pinkins in the second column, none of these are him. -18, -50, all exclusionary. And if you look at the column for Roosevelt Glenn, all exclusionary, negative numbers. 5 genotypes from the evidence. 2 were obvious. Another 3, well, certainly the last 2, produced by computer. And this is where we stood. And so that pretty much wrapped up my lecture at the Duquesne University Law School. And I got into my Uber ride, and this is what I was going to present. These were the findings. Unlike the human review that came before, the TrueAllele computer system in Pittsburgh compared evidence with evidence and got match statistics, not usually done by crime labs. It calculated exclusionary match statistics, not usually done by crime labs. It revealed 5% minor mixture contributors. That's almost never done by crime labs. It jointly analyzed DNA mixture data. Some labs are starting to do that, but it certainly was not possible 15 years ago. And it showed that 3 of the perpetrators were brothers. So now we have 5 unidentified genotypes. The defendants are not linked to the crime. Coded search is another lecture.
We never knew. We never found out.
It's not the role of government to solve crime. Because if it were, they would have run the coded search and found out who the brothers were. So that's why it's a different story. You might want to know, but nobody else really cared. We never presented the testimony because Fran called me on the Uber ride home and said, don't bother coming out. They agree with us. It's good science. There's no point in even bothering. And this is, I showed a picture of Darryl. This is a picture of Roosevelt. Roosevelt spoke at a conference that we had in Pittsburgh, as did Fran. And their talks are up on the Justice Through Science website. I'll show the URL in a second if you would like to see them. And as you've heard for only seconds, Roosevelt is an impassioned, emphatic, persuasive, emotion-inducing speaker. So it's a really good talk. It's the phrase, get out your handkerchiefs. It's very, very good. So I'd like to wrap up by just talking about a few broader issues. This is I think a 3-page magazine article that I wrote about the Pinkins and Glenn exoneration and the DNA evidence in Forensic Magazine. It's on our website. You can just type in the title of the talk. It'll come up online in Forensic Magazine. And it tells the story of what happened with the DNA, and it does it in a more merciful way that would take about 7 minutes to read instead of over an hour to endure in a spoken lecture. But it begins, and it just talks about what happened, what the DNA evidence was, and what it meant, and what the outcomes were. This is an article that I wrote that came out in The Champion 2 months ago. Anybody heard of The Champion? It's the almost monthly magazine of the National Association of Criminal Defense Lawyers, NACDL. Anybody heard of NACDL? They're a national organization of criminal defense lawyers. They have a magazine. I wrote this article maybe 2.5 years ago for another purpose, and I think it's on our website. It explains what happened for 20 years of total failure of crime labs to interpret DNA mixtures. What were the policies, what they knew, when they knew it, and really makes a case that most of this evidence for people who've been imprisoned, if there was potentially exculpatory evidence that showed that they weren't there, was never used in court because they didn't have the methods, or if they did, they didn't use the methods to provide exculpatory statistics. The data were called inconclusive, insufficient, too complex. That's still what's happening in most of the country. Now, the flip side of that, as we saw with no CODA search, is that evidence that could be used to find or convict the right perpetrator also hasn't been used. And so it comes down to a number of policy issues, choices made by the FBI and regulators in Washington to ignore the data that shows their methods didn't work. What happened in Washington is the FBI would decide, here's a great new method, we're using it. And then they'd publish a paper and tell the crime labs, you really need to start using this. Except if you go back and look at these papers, which are cited by lawyers as being peer-reviewed science, there's no data, there's no results, there's just an edict. Here is a protocol, follow it, it works. And then what would turn out is that it doesn't work. And studies done by the US government, as other agencies as described in this magazine piece, which is written for lawyers and not for scientists, it's pretty general, would show that it doesn't work. In fact, the main method that's been used on probably over 1 million DNA mixture samples for the last 20 years, called the combined probability of inclusion, can't work. And I wrote a paper on that, published it peer-reviewed 3 years ago, and showed on actual data as well as math why the method can't work. It's not that it doesn't work or that it can't be used in a more proper way. It's that it can't work. All it does is count up how many tests an analyst subjectively decided to use. So it's a random subjective counting procedure that has no correlation with identification information. And I can ask you, show of hands, what was the impact of the publication of this paper 3 years ago on policy in the forensic DNA community? Nothing. I mean, what does science have to do with what crime labs report about forensic evidence? Often nothing. And one of the problems is that the public is completely unaware of this problem. If you talk to people in the public, press, politicians, dinner parties, or me for another 5 minutes talking at you, you don't know that that DNA could work, but it doesn't work because crime labs choose to use methods that are simpler for them. At the invitation of an editor of our local paper, I sent in an op-ed article about the Pinkins and Glenn case, because I thought it was the most inspiring DNA case I had ever seen. Right? It's published in Forensic Magazine. They're on the news. Right? It's just an amazing story. And not the editor who invited me, but the op-ed editor wrote back was, So what you're saying is there's been advances in DNA testing, which we all know. Oh God, this is so boring. And the concept that yes, there have been advances in DNA testing that are not being used by almost any laboratory, that's news. I mean, penicillin may not be news, but refusing to use it and rejecting antibiotics, that's news. And to get that message out, well, maybe you can write somebody, call somebody, I don't know what you do. Sue somebody if you're lawyers. Litigate. We have a nonprofit in Pittsburgh that's trying some ways of getting messages out. We had this conference where you can see Fran and Roosevelt and other people. It was a very strange CLE conference. It was all day. What made it strange is it wasn't a prosecution conference, it wasn't a defender conference, it wasn't an innocence conference, it was everybody. This is a group of prosecutors that is so ethical that they will not prosecute a case with DNA evidence if their own in-house TrueAllele system shows that it's not the defendant. They just don't, they're not interested. They want real conviction. But we also had public defenders, we had defense lawyers, we had Greg Hampikian, who's always a hoot, Fran and Roosevelt. We had a mock trial, a judge, more scientists. The idea is that there is a community of people who do believe that forensic DNA is and should be an information science, not a follow protocols that don't work kind of bureaucracy. So take a look at that, and if you're interested in more information, if you happen to retire soon and have a year or two to read articles and watch YouTube videos, we've got a lot of content on our website. So thank you very much.